Okay, this is lesson 2.5, connecting rational equations to graphs of functions. And this is an extension to some of the work we did in 2.4. So the point of 2.4 was to simplify some rational expressions, and through the simplification, you saw that some of the restrictions that appear in the denominator may divide away. Some of the restrictions may not divide away, and they may remain in the denominator. So the point of this lesson is to kind of explore what those two restrictions behave like on a graph. So we're going to look at the two types, the ones that divide away and the ones that stay, and we'll kind of get our first look at what that might do to a graph of a rational function. So type 1, we'll start with the restrictions which divide away. The ones that divide away, when you simplify, create something called a hole. So to show you, I have a function. My function is x minus 1 times x plus 1 divided by x minus 1. As you can see, there is a restriction here. It's that x cannot equal 1. Because if we had x equals 1, 1 minus 1 in the denominator would give us 0, and we can't divide by 0. However, that restriction, that x minus 1, is common to the top and bottom here in factored form. So that restriction would divide away, and we'd just be left with x plus 1, with the restriction that x can't be 1. So we have to ask ourselves, well, after that restriction divides away, what are we left with? Well, we're just left with the equation x plus 1. X plus 1 is a linear function. It's a line, equation of a line. Slope of 1, y-intercept of 1. But what does this restriction do? Well, if we take a look at a table of values, we can start to build what this line would look like and then explore what actually happens when x equals 1. And the way I've done that is I've come up with a table here. I've picked these x values and generally pick numbers like -2, -1, 0, 1, 2. I've spread it out a little bit more. I've gone up by 2s. I started at -2 or -4, -2, 0. And then instead of going right to 2, I went to 1 because that's where the interesting thing might happen because that's our restriction. And I picked a couple numbers that were really close to 1, 1 on each side. And then I just continued with 4. Now, if we just use the numbers like -4, -2, 0, and 4, you'll see that it is just a line because it continues in a recognizable pattern. If we plug -4 into our function, -4 plus 1 is -3. -2 plus 1 is -1. 0 plus 1 is 1. And you can see we're just going up by 2 for every 2 that we go up on the x scale. And that kind of makes sense because this is a line with a slope of 1. If we start plotting these points, we got -4 gave us -3. So that's this point here. -2 gave us -1. So that would be this point. 0 gave us 1. And as you can see, we just are following a line. If we plugged in -6, we would have got -5. So we are following a line. So on this side of the graph, I'm just going to connect it and have a line. And since the equation is x plus 1, we'd expect this just to continue and have a line. If I plug in 0.9, 0.9 plus 1 is 1.9. 1.9 and 0.9, well, that's just before 1 and before 2, so we get a point that's kind of right there. That looks like it continues on the line. If I plug in 1, I get 2. However, x can't be 1. And restrictions are where the function's not defined because we can't use 1. It's a restriction. So the answer to what we would get if we plugged in 1 is undefined. However, when you simplify the equation, you end up with this. 1 plus 1, well, that is 2. So you can get an answer once you simplify. If we plug 1 into the original, you get 1 minus 1 on the bottom, which is 0, and you can't divide by 0. So that's the whole restriction business. So the correct answer is undefined, but in our simplified equation, if we ignore the restriction, we would get 2. And 1, 2 would also be a point that kind of fits that line. If we continue, 1.1 plus 1 is 2.1. And notice now that we're going up by 0.1s, the y's are also going up by 0.1s, which makes sense because it's a line. If we plug in 4, 4 plus 1 is 5. All these points fit the line. And because they all fit the line, and if we were to plug in 1 into the simplified equation 2, we would still fit the line, we just have a normal linear graph. And how we show this undefined at 1, the restriction that divided away, is with an open circle. There's my open circle. And then we can just continue the graph as a line. So a hole is represented on a graph by an open circle. So here we go. A hole at a restriction that divides away is just an open circle. And the rest of the graph would just be found by graphing the simplified equation. Keeping in mind that the restriction, the hole, is undefined, but you would put your open circle at 1, 2. So in this case, we have a hole at 1, 2. That's our first type of restriction. Now, the second type of restriction is one that doesn't divide away. So let's go look at one of those. So let's pretend we had a more complicated rational equation, and we simplified it, and we ended up with something like this. 1 over x minus 2. Now, this looks a lot like the parent function 1 over x that we saw in the first unit. The only difference is that we have this minus 2 acting on x, which is just a transformation of the original parent function. And since it's being subtracted from x, that's a shift to the right of 2. So what you would expect from a graph of this function is the original parent function 1 over x shifted to the right 2. And that's something we kind of explored in the last unit. So if we look at this in terms of restrictions that don't divide away, we now know that there's a restriction to this function. X cannot equal 2. 2 minus 2 is 0. So we're going to have some sort of behavior at 2. If we think about the original parent function 1 over x, it's the one that had the curve in this quadrant and the curve in this quadrant going through negative 1, 1 and 1, 1. And it had a vertical asymptote along the y-axis and a horizontal asymptote around the x-axis. Now, that vertical asymptote, 1 over x, so that would be x is 0, that vertical asymptote is what the restriction does when it remains in the denominator. It creates an asymptote. So if you have a restriction that remains in the denominator, in this case 2, we get an asymptote. An asymptote at x equals 2. So I'm going to add that to my graph. And then I'm going to show you how and why based on points around 2. There's my vertical asymptote. So let's plug some numbers into this function, get some y values, we'll plot them, and then you can kind of see how we know this is an asymptote and not a hole. So negative 4, if we plug it in, we get 1 over negative 4 minus 2 is negative 6. 1 over negative 6 would just be negative 1, 6. If we plug in negative 2, we get negative 4 on the bottom. So we have 1 over negative 4. If we plug in 0, we get negative 2 on the bottom, negative a half. We'll skip these ones for a second. If we plug in 4 on the bottom, we get 1 over 4 minus 2, which is 2, which is a half. If we plug in 2, 1 over 2 minus 2 is 0 on the bottom. 1 divided by 0 is a math error in your calculator, which means undefined. These numbers all appear normal. They appear to follow a pattern. It's when you get really close to the undefined that we see something unique. Now, when we looked up here at the numbers like a whole, they kind of continued with the pattern. These numbers were going down by 2 when we were going, the x's were going down by 2. When we started going down by 0.1, the numbers went down by 0.1, or up by 0.1s as it was. Something weird happens when we get really close to the undefined when it's an asymptote, not a whole. If we plug in 1.9, 1 divided by 1.9 minus 2 would be 1 over negative 0.1, which is negative 10. That number explodes. These numbers are quite small, all under 1 on the negative side. All of a sudden, we're at 10. That number exploded. On the bottom, 2.1 minus 2 is 0.1. 1 divided by 0.1, well, that's 10. That number is also huge. As you can see, as we get close to that undefined, these numbers take off. These numbers are huge compared to numbers like a half and negative a half that are just 2 units away. When we get really close, these numbers get bigger. In fact, if we got even closer, if we did 1.99, the answer would be negative 100. If we did 1.9999 and we got closer and closer and closer, this number would get even bigger, like negative 1,000,000 if we added enough nines to our decimal. So the closer we get to our undefined, these numbers actually explode. Up here, when we were looking at our whole, the closer we get to 1, the number is just going to get closer to 2. It's not going to explode in any one direction. It's just getting really close to 2, which is getting really close to the whole. For a vertical asymptote, when you get really close to it, the numbers get very extreme. They shoot off the graph. And that's what happens when we go to graph this. If we graph these points, negative 4 and negative 6 would be a point like right here, negative 2 and negative 1/4, 0 and negative 1/2, and then 1.9 and negative 10, 1.9, negative 10, it shoots way down the graph, and all of a sudden we're down here. So the graph was here, and it wasn't moving very fast. It was getting slowly and slowly lower and lower and lower, and then all of a sudden we get close to this asymptote, and boom, we start approaching the asymptote and shoot off the graph. And that's what behaviors around asymptotes look like, and that's a huge topic in advanced functions when we get to rational functions and advanced functions. So we don't need to have a full understanding of this right now. It's something that we continue to explore. But what I would like you to know is that if the restriction remains in the denominator, it means you have an asymptote, and if the restriction divides away, it means you have a whole. That's the takeaway. Let's just finish this here. 2.1 on this side would be 10, so we have a point way up here, and then all of a sudden at 4, we're all the way down to a half. So as you can see, it's dropping very quickly. And if we plugged in more numbers, we'd see they just keep approaching 0. So this one doesn't divide away, it remains in the denominator, and we end up with a vertical asymptote at x equals 2. So one last time, just to summarize, if the restriction divides away, we get a whole. To find out the coordinate of the whole, you can simplify the equation and then plug in the restriction to the simplified form. 1 plus 1 is 2, so our whole is at 1, 2. If it doesn't divide away and the restriction remains in the denominator, that restriction leads us to a vertical asymptote at whatever that number is. So to consolidate, let's take a look down here. I've got a rational function that has not been simplified. What features of the graph would this function have? Well, we have 3 restrictions. X can't be 1, -1, or 4. I'm going to write those in order. -1, 1, and 4. Those are all the values that make 0 in the denominator. A couple of these divide away. Common factor on top and bottom, common factor on top and bottom. 1 and -1, the ones where the restrictions give you 1 and -1, divided away. And the one that gave us a restriction of 4 did not divide away, it stayed in the denominator. So that should tip us off as to what type of restriction we have. If we simplify this equation, we end up with x minus 2 on top, x minus 4 on the bottom, with our restrictions, -1, 1, and 4. What features would the following equation have? Well, 2 of them divided away, 1 and -1, so those would lead to holes. So we'd have holes at -1 comma something and 1 comma something. And we can figure out what those something are. And we had one that didn't divide away, so that's a vertical asymptote. And it's the 4, so it's x equals 4. So let's consolidate here one more time. Vertical asymptotes are the ones that don't divide away. Holes are the ones that do divide away. We know the equation of the vertical asymptotes, x equals 4, because that's the restriction. If you want the location of the hole, you take the x value of the hole and plug it into your simplified equation. If we plug in -1, we get -3 on top, -5 on the bottom, which should be 3 over 5. If we plug in 1 to the top and bottom, 1 minus 2 is -1. 1 minus 4 is -3. We get -1/3. Nope, +1/3. 3/5 and 1/3. -1 and yep, nice. So holes and vertical asymptotes. Holes are the terms that divide away. Vertical asymptotes stay. That's the takeaway. All right. Thanks for watching our extension lesson, lesson 2.5. I'll see you next time for 2.6.